We've learned how to calculate the first derivative using the power rule. Now we're going to expand further to include the constant times a function rule that we already implemented a little bit, and then also the sum and difference rule. They are both listed here, but just as sort of a shortcut way to describe them. What this means is if we have something like y equals 3x to the fourth, this constant out front, nothing changes in terms of that. That just means we can multiply this, and our first derivative is going to be 12x to the 4 minus 1, which is 3. If we have something where things are being added, then we can just add their derivatives. For example, if we have y equals 3x to the fourth plus 2x squared, we've already taken the derivative of this above, so y prime is going to be 12x cubed, and then we'll take this derivative as well, and it will become plus 4x when we multiply this and then subtract 1 from the exponent. Let's look at some other examples of these first derivatives using these rules. If we have y equals 5x squared, that exponent comes out front, and y prime becomes 10x to the first. Again, subtract the exponent. If we have y equals negative 4x, this is an understood exponent of 1. We're going to bring it out front, and y prime becomes negative 4x to the 0, or just negative 4. Remember, this is a line, and thus the slope of the tangent line, which is what the first derivative is, will be a constant number, which is negative 4. Applying the addition and subtraction rule, if we have 5x squared minus 4x, we're going to calculate the derivative of each piece. Y prime, therefore, will become 10x to the first, and then this is an understood 1, so we just end up with minus 4. Don't let fractional exponents and more complicated looking equations bother you. If we have y is equal to x cubed plus 8 times the square root of x plus 2 over x, it is important to know your rules of exponents. The first derivative here I can calculate fairly easily. Y prime on that part is going to become 3x squared, but it may be easier to think of this as 8 times x to the 1/2. And then I apply the same rule. 8 times 1/2 is going to give me plus 4. X to the 1/2 minus 1 is going to give me negative 1/2. And then likewise, if I think of this as 2x to the negative 1, I can then bring that negative 1 out front, and I get minus 2x to the negative 2 when I subtract. And then we can rewrite these as 3x squared plus 4 over x to the 1/2 to get rid of the negative exponent, minus 2 over x squared. And then finally, we can even adjust that x to the 1/2 to be the square root of x minus 2 over x squared. It may be helpful to multiply things out before finding the derivatives. For example, if we have something like f of x is equal to x to the 1/2 times x squared plus 2x, apply those rules of exponents to multiply out. So then you can apply the sum and difference rule. This is going to give us x to the 5/2 when we add our exponents, plus 2x to the 3/2. We can then apply the power and the sum and difference rule, which leaves us with 5/2 x to the 3/2 when we subtract, plus 3x to the 1/2 when we multiply and subtract there. Do not let those negative exponents or things in the bottom throw you off. If I have perhaps g of x is equal to x squared plus 1 over the square root of x, I can think of this as x to the negative 1/2 times x squared plus 1, which gives me x to the 3/2 when I add the 2 and then negative 1/2, plus x to the negative 1/2 when I distribute. And therefore my g prime, that first derivative, is going to become 3/2 x to the 1/2 minus 1/2 x to the negative 3/2. As a reminder, the derivative can be thought of as the slope of the tangent line. And then once we know the slope, we can find the actual equation of the line at given points. For example, if we have a function 8x minus x squared, we can use the first derivative to find the slope of the tangent line anywhere along that line. Given that f of x is 8x minus x squared, the slope of the tangent line, we're going to apply our rules, is going to be 8 minus 2x. Now I can find the slope of the tangent line at 2 by plugging in 2 for x into my first derivative equation, which gives me a value of 4 for my slope here. I can find the first derivative at 4. Again, 8 minus 2 times 4, which is going to give me a slope of 0. And last but not least, I can find the slope when x is 5, 8 minus 2 times 5, which leaves me with a slope of -2. Now that I know the slope at each of those locations, I can find the equation of the tangent line. Remember, a line is of the form mx plus b. In our first case here, I know this slope is now 4. But then I also know a point. I know when x is 2 on the curve, I can go back to my original equation and plug in 2. And when I do that, I get a value of 12. And then solving for b, I get a b value of 4. And thus my tangent line where x is 2 is going to be 4x plus 4. And you'll notice here, this is the curve. If I go to where x is 2, then the slope of that tangent line was 4, and the equation itself was 4x plus 4. Doing the same calculations here, I know that the slope was 0. And therefore, when x is 0, if I plug 0 into my original equation here, I get the value of the function when x was 4. The slope was 0. When I plug in 4 to that equation, I get that y is going to have a value of 16. So 16 is going to be b. And again, that equation is of the tangent line at the point 4, 16 on the original curve. And last but not least, if I know the slope is -2 when x is 5, then I can plug in my value. When I plug in 5 to my original equation, I get a value of 15 for y. So I have -2 times 5 plus b, giving me a b value of 25. And so my equation is going to be y equals -2x plus 25 at the point here. An area where first derivatives are used in particular is that of velocity and distance. Remember, we have talked about the idea that distance as a result of time, if we take the first derivative, that first derivative is going to be the velocity, the first derivative of distance, because velocity is nothing more than the change in distance over the change in time. If we are given equations such as this, where we have a boat and the distance is described by t to the third plus 60t, then we can use the first derivative, s of t, which is equal to the velocity, and in this case would be 3t squared plus 60 to calculate the velocity at any given moment. In A, we're trying to find the velocity at the starting point, which would have a value of 0 for time. Plugging in 0 for t, we get an initial velocity of 60. Likewise, if we want to find the velocity at 3 minutes, we can plug in 3 to our velocity equation. We're going to have 3 times 3 squared plus 60, which gives us 27 plus 60, or 87. And note, in all of these, the derivatives are giving us a value per something. In this case, it's giving us a value of meters per minute in both cases.